Swayam Prabha. Digital India. Educated India.
Hello and welcome to this course on gas turbines and jet engines. So, today is lecture 12 of this course. So, this is the second lecture of week 3 and today we are going to solve some numerical problems on the previous two topics, which were intercooled cycle and combined regeneration intercooled cycles. So, we will see how to solve problems for these cycles, and that is not the only purpose. We will also try to see what sort of values we obtain for realistic values and for the same set of design parameters which we have used for other types of cases, and then we can have a comparison of these values to see how the efficiency and the work output changes for the same set of parameters when the cycles are changed to intercooled cycle or regeneration intercooled cycle. Okay. So, concept which will be covered: solving problems for both intercooled cycle as well as intercooled regeneration combined cycles. Before we start with solution of a problem for the intercooled cycle, okay, and intercooled regeneration cycle, I just wanted to show in general what type of problems we had solved previously, okay, for other cases. So, I have taken an example from a regeneration cycle to show that these parameters that we had taken were inlet air condition of or ambient temperature of 3000 Kelvin and maximum temperature or turbine inlet temperature as 1500 Kelvin, pressure ratio as 10. Okay. And if regenerator is present, as was in this case, we always assume that for these ideal cases we assume that the effectiveness is 1. Okay. And then from this we calculate what is the net work output and efficiency, and for that case we had obtained 61.4% efficiency, okay, and it compared with the simple Brayton cycle efficiency of 0.482, and for reheat it was 0.419. Okay. So, we will keep the same framework for intercooled Brayton cycle and for the regeneration plus intercooled Brayton cycle, but see how the values change, okay, because of the change on these processes. So, let us start with intercooled Brayton cycle problem. Okay, we will call this problem as problem number 5 if we are going chronologically. So, this is the 5th type of cycle we are numerically analyzing. So, we will draw the TS diagram as always. This is the best way to start solving any of these problems. Then let us quickly draw the intercooled cycle. 1 to 2, 2 to 3 is the intercooling, 3 to 4. By this time it should be very familiar to you because we have discussed this multiple times. 3 to 4 is the high pressure compression. If it is not familiar, please pause and go back to the previous lectures and try to get a good understanding of this process. Okay. So, this is 5 after the conversion process and expansion in the turbine leads the air to state 6, and 6 to 1 is hypothetical heat removal process for closing out the cycle. Okay. So, the conditions which are given to us is ambient air temperature is 300 Kelvin. Like for all the other cases, we are taking same values for each case. Why? Because although we will learn the solution of or the procedure of solution, we will also be able to compare the results directly with all the previous types of cycles because of the same values, and that is very important for us. Okay, so, the pressure ratio is 10 and maximum temperature or turbine inlet temperature is taken as 1500 Kelvin. Okay. And of course, air is the fluid which is being circulated through the cycle, okay, and air is assumed to be ideal gas. Okay. So, in almost all cases we will assume air to be the working fluid, because in real life application also this is air and for part of the cycle, and then we have conversion products, but those are also diluted and contain significant amount of air. Okay. So, T max is equal to 1500 Kelvin, and with this we want to find out what is the efficiency as usual and what is the net specific work output of the cycle. One additional condition that has been given here is that the regenerator, not the regenerator, the intercooler operates at or has been designed with optimum condition. Okay. So, intercooler is at optimum condition. At optimum condition. What does this mean? So, this means that both the compression processes have equal pressure ratio, okay, like what we have derived for the intercooling cycle. Okay. So, P 2 by P 1 is equal to P 4 by P 3, that we already know. P 2 by P 1, which is equal to root of R. So, now how to proceed? Procedure is exactly same. So, I always encourage that you should not use any of the expressions as formula. Expressions were derived to understand the characteristics and plot the characteristics, but when solving numerical problems we go step by step through each process, find out the important parameters which are needed at each state, for example, temperature at each state, and from that we can calculate all the energy transfer values. So, in this case the net work output W net I am directly writing. So, this is W T turbine work output, okay, going from 5 to 6 minus compressor work input for the first compressor minus compressor work input for the second compressor, okay, from 1 to 2 and from 3 to 4. What additional conditions are known to us? We know that T 3 is equal to T 1, and because of the optimum condition T 4 is also equal to T 2. Okay. So, now this means that for net work output, see W T is C P T 5 minus T C. Let us write down for this case, because this is at the start of the course. I am going a little slowly, so that you have sufficient time to follow the topics. C P T 2 minus T 1 minus C P T 4 minus T 3. What is the value of T 5? Already known to us, T 5 is 1500 Kelvin. Again I will remind you that do the problems or solve the problems in Kelvin to avoid any chances of error. Okay. So, T 6, what is the temperature T 6? So, T 5 by T 6 is equal to 1 by, sorry, not 1 by, let me correct. T 5 by T 6 is R to the power gamma minus 1 by gamma, where R is equal to 10 and gamma is 1.4. So, this gives us a value of 1.9307. If you pause here and go back to the previous problems, you will see that we had obtained the same value for these cases, okay, when there was no reheating, which means that T 6 is equal to 776.92 Kelvin. Okay. So, this is 776.92 Kelvin minus Cp T2 minus T1. What is the value of T2? Remember, T2 by T1 is R A, okay, for the first compressor, to the power gamma minus 1 by gamma, which is equal to root 10, okay, root of R to the power gamma minus 1 by gamma. So, this comes out equal to 1.389, which gives us a value of T2 equal to 416.85 Kelvin. Okay. So, 416.85 minus 300 minus Cp into. So, T4 is equal to T2 and T3 is equal to T1. So, T4 minus T3 is equal to T2 minus T1. So, we have the same value again, 416.85 minus 300. Remember that we are taking Cp value to be equal to 1.005, standard value for air at atmospheric condition, standard atmospheric condition, 1.005 kilojoule per kg Kelvin. Always focus on the units, units are very important. So, we should not, so you should always write the units for any of these values and try to see that the units are correctly defined. So, this gives us a overall value of 491.83 kilojoule per kg. You can pause here and again go back and check with the previous problem what sort of values we had obtained for the other cases. Okay. So, to give you some perspective, for the standard case the work output was 446 kilojoule per kg. So, this is significantly higher than the standard Brayton cycle. However, for the reheat cycle the work output was considerably higher, it was 564.5 kilojoule per kg. So, here the effect is not as strong as adding reheating, that we have already discussed that intercooler does not have as drastic effect as reheating, okay, both on the positive side as well as on the negative side. So, finally, we can find the efficiency. Is the net work output by heat addition. Heat addition in this case is Cp T5 minus T4, Cp T5 minus T4. Okay. So, W net we have found 491.83. Cp we already know 1.005 kilojoule per kg Kelvin. T5 is the maximum temperature 1500 and T4 is equal to T2, right. So, T4 is equal to T2, which is 416.85. Okay, so, this is 1500 minus 416.85. So, we get a value of 0.452 or 45.2%. Okay. So, if you compare this, you will see that the efficiency is lower slightly than the standard Brayton cycle. Okay. We will do a comparison later on in today's class. However, this is higher as compared to the cycle with only reheat, okay, because we have seen that the effect of intercooling is not as drastic. Okay. So, now we move on to the other problem. We will see how these values compare with all the previous cases in tabular form later in today's class, okay, once we solve another problem related to intercooled plus regeneration cycle. So, we will take the second problem. So, this is overall problem number 6. Let us use something else, the color. So, combined intercooling and regeneration. Intercooling plus regeneration. Okay. All the conditions remain same. So, ambient temperature is 300 Kelvin. All these cases are all the conditions are same as the previous problem, except that we are now adding a perfectly effective regenerator, means regenerator with effectiveness equal to 1. R is equal to 10, maximum temperature T max is equal to 1500 Kelvin, and we have added another condition that we have a regenerator with effectiveness 1. Okay. And of course, the working fluid is air at standard atmospheric condition, okay, which we will use constant property values as usual for ideal cycles. So, in this case again we want to find out what is the net work output and efficiency. We could have devised the problems in different ways also, but the purpose of making this problem all of these look similar is that we can do a direct comparison for the same set of values or same set of design parameters T A and R. We can do a direct comparison of the performance of each of the cycle, okay, in terms of the net work output and efficiency. Later on we can try problems with other types of variations, okay, or different types of problem constructions also. So, let us do a better job. So, 1 to 2 low pressure compression, 2 to 3 intercooling, 3 to 4 high pressure compression, 4 to 5 is the overall heat addition. So, after regeneration plus combustion, 5 to 6 is the expansion in the turbine. Then the regeneration processes, regeneration, if we assume that we have ideal or perfectly say effective regenerator, then we go from 4 to 7. So, the air from the compressor outlet goes to temperature T 7 because of regeneration, and the corresponding air the combustion products from the turbine exhaust go to 8. So, T 7 for ideal case T 7 equal to T 6 and T 8 equal to T 4 equal to T 2. Okay. So, these are the regeneration process, and we are closing out the cycle from 8 to 1. So, we can write then that for perfectly effective regenerator, T 7 is equal to T 6 and T 8 is equal to T 4, and for optimum intercooling this is also equal to T 2, which we have previously discussed. Okay. So, now the solution process is exactly similar, and our main aim is to see what are the values we obtain of net work output and efficiency. Okay. So, in this case again we go step by step, find all the temperatures. from the previous problem we already know. Anyway, T A is going to be equal to T 1 is going to be equal to T A, which is 300 Kelvin. T 2 we have derived in the previous problem, okay, that will be the same value of T 2 will be there. So, if you go back, we have derived that T 2 is 416.85 Kelvin. Okay. Same, because it is the same pressure ratio at optimum condition, T 2 by T 1. Okay, let us write down here as rough. T 2 by T 1 is root r to the power gamma minus 1 by gamma. So, this is 416 0.85 Kelvin. Then T 3 is equal to T 1, which is 300 Kelvin, and T 4 is equal to T 2, which is again 416.85 Kelvin. Okay. We found half of the values. T 5 is known to us. T 5 is the maximum temperature, which is a design input parameter called turbine inlet temperature, as we had discussed, or maximum temperature of the cycle. Okay. Then T 6 again for the same expansion as the previous case, T 6 also should be similar. So, T 5 by T 6 is equal to r to the power gamma minus 1 by gamma, and using exact similar process we will obtain T 6 to be equal to 776.92 Kelvin. 776.92 Kelvin. T 7, because the regenerator is ideal regeneration, T 7 is equal to T 6, which we have already stated. So, this is equal to 776.92 Kelvin, and T 8 is equal to T 4 or T 2, which is equal to 416.85 Kelvin. So, now we have the temperature at all the states. So, there are 8 different states considering all the processes, and we know the temperature at all these 8 states. Now, we can directly use them to find the values of net work output and efficiency. What will be the net work output? Is it going to change from the previous problem? It is not going to change from the previous problem, because when we add regeneration, there is no change to the work output from the turbine or work input in the compressor. Okay. So, net work output will remain same. Okay. So, in terms of expression, it is C P T 5 minus T 6 minus C P T 2 minus T 1 minus C P T 4 minus T 3. And we had already calculated these values and had the exact same values of T 5, T 6, T 2, T 1, T 4, T 3. So, this came out equal to 491.83 kilojoule per kg. Okay. 491.83 kilojoule per kg. Now, what about the heat addition? Heat addition is going to change, because regeneration leads to or enables us to use less heat addition in the combustion process. Okay. So, this heat addition now is C P T 5 minus T 7, and we know what is the value of T 7. T 7 is equal to T 6 equal to 776.92. Okay. So, 1.005 into 1500 minus 776.92. So, now you get a value of the heat addition. Okay. So, this is equal to, so this we will not have in the previous problem, because this will be different. This is equal to 726.695 kilojoule per kg. Compare this to the previous problem where there was no regeneration. Okay. So, I have although we have not exactly found what is the value of this, we can try to find, and if you find it, you will see that this is equal to 1088.6 kilojoule per kg, the heat addition. Now, it has decreased because of regeneration by a significant amount, okay, by about 1/3 of the amount of heat addition previously required. Okay. So, finally, we get the efficiency as net work output by heat addition. So, this comes out to be very high value of 67.7%. Okay. Like I was saying, regeneration and intercooling together are very effective, and as a result we get very high efficiency, and we will see that although in all cases the effect of reheat is stronger than intercooling, but for this case where the efficiency is in concern, where we are concerned about the efficiency, in this case intercooling increases the efficiency more as compared to reheating for this regeneration cycle. If I add an intercooler to regeneration, we will get higher efficiency as compared to reheating. Okay. Now, let us compare these values with all the existing values. So, standard cycle, okay, we had, so all these are based on our calculation. If you want, you can revisit any of these problems from all the previous lectures. Okay. We have solved 6 problems based on the same design parameter values and obtained the equivalent performance characteristics, so that we can directly compare them. So, standard we have 446 kilojoule per kg. If I compare the work output, regeneration of course will not change it. Reheat was used for increasing the work output, and it significantly increased. So, this became 564.54, and of course, the same will be value for regeneration plus reheat. Now, when intercooling was added, or if it is an intercooled cycle, then the value is in between that of reheat cycle, means reheat cycle and standard cycle. Okay. So, we obtained a value of 491.83, which means that we get considerably higher value than the standard cycle, but still we do not have as much penalty, as we will see later, compared to reheat cycle in the efficiency. Okay. And finally, for intercooling plus regeneration, we of course will have same work output, which is intermediate, or like a value in between the reheat plus regeneration case and the pure regeneration case. So, if I compare these two, pure regeneration 446.08, reheat added to regeneration 564.54, intercooling added to regeneration 491.83. Okay. For the efficiencies, standard cycle 48.2, remember these values are high because these are all ideal cycles with actual losses, these values will come down considerably. Okay. Regeneration increase the value to 61.4%, reheat of course will decrease the value even much below the standard cycle. So, we obtain 41.9%. So, we can compare the reheat case with the intercooled case, and we see that the penalty on the efficiency is not as severe. So, although intercooled cycle also has lower efficiency as compared to the standard cycle, the decrease is much less as compared to that for reheat cycle. Okay. Then we had seen that reheat and regeneration are very effective, and counterintuitively we get a higher, not counterintuitively, but in contrast to say the effect of pure reheating, adding reheating to regeneration increases the efficiency even much beyond the efficiency of simple regeneration cycle. Okay. So, we obtain 66.8%, which is a very high value, although this is theoretical, but adding intercooling even surpasses that. So, we have till now whatever is the highest value obtained has been obtained by intercooling and regeneration. Okay. So, we get moderate increase in the work output and get very high increase in the efficiency. So, that is why we were discussing that intercooling plus regeneration is a very effective combination. Okay. This is even higher as compared to the regeneration plus reheat case. So, here the effect of intercooling is stronger in increasing the efficiency of regeneration, unlike say for pure intercooling and pure reheat cases. Okay. So, with this we will conclude today's class. So, in this class we have learnt the procedure to solve problems related to intercooled gas turbines and combined intercooled gas turbines combined with regeneration. And not only that, we also found the values of the performance parameters, efficiency and work output for given set of design parameters and compared the values with all the other cycles we have discussed till now for same values of design parameters, and we have seen how the efficiency and work output is different from the other cases. We have seen that efficiency is highest among all the cycles discussed till now, whereas the work output is in between two extreme cases. So, it is intermediate between the reheat cycle and the simple Brayton cycle. Okay. So, these are the references and you can refer to the number 1 reference top book or the second book for direct background study, okay, and some of the other books also for reference material or problem solving. I hope that you have started solving the assignment problems, start practicing the assignment problems and the additional problems which are given. Okay. So, with this we conclude today's class. Thank you, and we will meet again in the next class. Thank you.